In this video, we're going to continue analyzing data by looking at measures of dispersion. We're going to focus on how we can calculate the measures of dispersion for discrete and continuous data, and then look at how we can use that information to identify outliers. We should begin by clarifying what is meant by measures of dispersion. Pictured on your screen are three histograms representing three distinct data sets. All three data sets are symmetrical, and all of them have the mode clustered right in the center of the data set. If you were to calculate your measures of central tendency for these data sets, it's not unlikely that the mean, median, and mode would coincide for all three of them. The measures of central tendency here do not paint the complete picture. Although the measures of central tendency fall largely within the same place for all three distributions, it's quite clear to us that the graph on the left represents a data set where more of the data is clustered towards the center, whereas the graph to the far right represents data that seems to be spread out further across the full range of data. So while our measures of central tendency help us focus on that peak in the center of a distribution of data, our measures of dispersion actually let us focus on what's happening towards the fringes or extreme values of a data set. The first measure of dispersion we use to get a sense of what's happening towards the fringes of a data set is the range. The range is the difference between the maximum or largest value and the minimum or smallest data value. And we find it by just subtracting one from the other. This statistical measure is really helpful because it lets us know how spread out the entirety of the data set is. Being able to look at the range allows us to establish consistency. If the range is very small relative to the variable being measured, that means that the data tends to be very consistent, and it means our predictions based on that data are likely to be more reliable. The flip side of that is, if the range happens to be very large, especially relative to the value being measured, it means the data is not very consistent, and predictions made based on that data were not as certain that they're going to bear out. We need to be extremely cautious about using the range as our only measure of dispersion, because, like the mean, it is incredibly susceptible to being skewed. If our minimum or maximum value is very far removed from the general clustering of the data set, perhaps even being an outlier, the range will give us an incredibly misleading value of the spread of the data. To dig further into the idea of measures of dispersion, we also will explore the notion of quartiles. Quartiles are values that divide your data set into four sections, each containing an equal portion of the data. There are three key quartile values: the lower quartile, or Q1, the middle quartile, or Q2, and the upper quartile, or Q3. Now, the middle quartile is the same as the median. It splits the data set into a lower 50% and an upper 50%. The lower quartile and upper quartile just further divide those regions in half, and so each of those regions then represents 25% of the data. Although they appear to be evenly spaced in this diagram, it's important to note that these quartiles are not a fixed distance apart from each other, but they do split the data up so that the data is evenly distributed between the quartile values. The reason why determining the quartile values can be helpful is because we can then calculate what's called the interquartile range, which is the middle 50% of the data. It's that first 25% that's less than the median, and then the first 25% that's greater than the median. This is a much more reliable statistical measure because it's less likely to be skewed by those extreme values on the fringes of the data set, the minimum or the maximum value. By staying clustered towards the central 50% and looking at the spread of those values, we can still look at our measures of dispersion without being susceptible to skew from those outliers. In order to get a better handle on these measures of dispersion and how you would calculate them, we're going to actually look at an unsorted data set here and determine those measures of dispersion by hand. First, I must sort the data set so I can determine my measures of dispersion. We cannot accurately determine how the data is distributed until we have put it into ascending order. The median value for this data set is 6.5, so that will be our middle quartile value. You'll notice that while 6.5 is not a value in our data set, that is the value that will evenly split the data set into two equal portions, with 10 values below the median and 10 values above. By splitting these ranges in half, I'm able to determine the value for Q1, which is 5, and Q2, which is 10. You can see here that my quartile values have split our data set up into 4 equal chunks of 5 data values each from the original 20 numbered data set. With an ordered data set, I can determine my range by subtracting the maximum and minimum values. Here I'll get 18. And then I can also calculate my interquartile range, where I do the upper quartile minus the lower quartile. And in this instance, that's going to get me a value of 5. So here I have the range and interquartile range as 18 and 5 respectively. This communicates to me some information about how the data is distributed and how consistent it happens to be. These values are helpful to a point, but where having the range and interquartile range really shines is if I can compare two data sets and establish which of the two happens to be more consistent. Knowing the quartile values does help me get a sense of how the data happens to be skewed one way or another. If I look at the distance between the minimum value and the median, it's only a range of 4.5 between those values. If I go from the median to the maximum, I see that that is a range of 13.5 in my data set. So it looks like the data is much more spread out in that top 50% and much more clustered together in the bottom 50%. Now, while this data set isn't based within a context, if I was to observe this in a contextual setting, that might be really illuminating in terms of understanding how the data is spread out in one area versus being clustered together in another. And I might be able to make some really interesting observations then about what that means in a context. Context or no, seeing how spread out the data is in that top 50% has me wondering whether we have the presence of any outliers in our data set. Specifically, the 20 at the high end of the data set looks to be a bit high relative to everything else. But I can't just determine that it's an outlier by eye. We need to actually have a reliable method and a calculation that we can use to peg a data value as an outlier definitively. The way that we do that is using our quartile values and our interquartile range. We can identify data values as outliers by comparing them to these measures of dispersion. So if I have a data value x and it happens to be less than the lower quartile minus 1.5 times the interquartile range, then that would be an outlier. Similarly, on the high end of my data set, if I have a data value that is greater than my upper quartile plus 1.5 times my interquartile range, then we would designate that value as an outlier. If I calculate the values then that correspond to the lower bound and upper bound that define what an outlier is, it's going to help me determine which of these values should be flagged as outliers and which ones shouldn't. So I've done the calculation for my lower bound on the left side of the screen. I got negative 2.5 here, so any value less than negative 2.5 would have to be considered an outlier. Now, my smallest value in the data set is a 2, so obviously this lower bound doesn't come into play in terms of flagging an outlier. At the other end of the data set, I've calculated the upper bound for what determines an outlier and came back with a value of 17.5. Now, my value of 20 is bigger than that, which means that I would need to flag it as an outlier. Now that we can understand our measures of dispersion in a mechanical way, it's time to reintroduce the notion of a context. So we're going to revisit that data set we had involving Franny's restaurant and parties coming in to dine at the restaurant on Saturday evenings. In our last video on measures of central tendency, we looked at this data to calculate the mean, median, and mode. But now we're going to go a little further and calculate our measures of dispersion as well. Fortunately for our purposes, the steps that we actually take on our calculators to determine our measures of dispersion are no different than the steps we use to find measures of central tendency. Your minimum value, maximum value, and your quartiles, Q1, the median, and Q3, are all present on your one variable stats screen. We didn't have a use for them earlier, but now we can, and we have a use for them. So when you do your one variable stats calculation after entering this data in as you normally would for measures of central tendency, you'll also be finding your key measures of spread. For this data set, our Q1 is 4, our Q2 or median is 5.5, and our Q3 is 7. The piece that's most interesting about this data and the measures we've now calculated, if you look at Q1 and Q3, they're both equally distant from the median. And so this suggests that middle 50% of the data is actually distributed pretty symmetrically around those measures of central tendency. Here I've presented a data set involving continuous data, and I want you to practice calculating measures of central tendency and measures of dispersion. Remember, the method for entering this into your calculator to determine these values is no different than what you did for measures of central tendency, and so this should be a well-practiced skill at this point. Here are the correct measures of central tendency and measures of dispersion that we were looking for. We can tell by looking at these that the data here is also very clustered towards the center based on the mode. We can also see that based on the interquartile range being 20, and that's actually 10 units in either direction around the median, again, there does seem to be a lot of symmetry to this data set. Now that we know how to determine measures of dispersion by hand and with our calculators, we should be able to determine these statistics based on any data set provided and start to think about what conclusions we can form about the reliability and consistency of the data based on those measures of dispersion.